3.4, the derivative as rates of change. So let's take a look at this. The next section. So we talked about the derivative being slope of a tangent line, which is of course true, but you can also think of it or look at it as just as a rate of change, and specifically an instantaneous rate of change. So let's define that and talk about it. So the definition of this is really the same thing. When we say for a function f, if we have f prime of x naught equal to the limit as h approaches 0 of f of x f of x naught plus h minus f of x naught all over h is defined to be the instantaneous rate of change. And I'll explain it a little bit as we go. Rate of change. Okay. So if f of x is a position function, and so you think of it, it really is just a function, but think of it actually as like a moving particle. Okay, so if f of x is a position function, written as, and this is just some notation stuff, so it's written as basically we use s of t or f of t. And this, again, is just like, so we think of it as time. So now we're going to consider a curve, and it is with respect to time. So you have some curve like this, and as it's being traced out, we can say that there's a starting point and an ending point. Oops, I want to erase everything. So if you have, start like that. Okay, so suppose that's like, that would be like t naught is where you start here. And then as t increases, this could be like t2, t1, and then t2. You're tracing out from the particle like that, and then it might just take off. So in previously, when you say like f of x, x is defined on the reals, it's really just like it's always there. Like there's no start and end. It's just that's what it is. But for when you think of it as a position function, you could think of it as the rate of change, or place the car is or something. Okay, and think of it as like a general particle, really. But that's what we're looking at. So then, if you look at delta s, the change in s over the change in t, that is going to be f of t, t plus delta t minus f of t all over delta t. Okay, so that is basically the slope of that, and it's like the secant. And that's, so this is your, so if this is just t, this would be the t plus delta t. And then the difference here is your difference of your function values. This is difference of your function values. This is difference of your t values, or you're incrementing delta t. So that is what we refer to as average rate of change. Average rate of change. Okay. So that's considered your like speed, velocity, and we get more into that much more later, and also in physics. It's defined a little better, a little more carefully. So, so if you're like, so the idea here is, if you're like driving from here to say Vegas, so you're going to Vegas. Can't do much these days in Vegas because I made this during COVID. But anyway, you're going to Vegas. You let's just show you what I mean. I always show this in class. So you're here. You take off. You get on the freeway. You speed up, and then you get to a speed, and then you got to slow down for a truck, and then you got to pass the truck. So you speed up, and then you slow down again to your average speed. Whatever speed you'd like to travel at. Okay, so you're traveling at a certain speed, you're cruising, you're going pretty fast, you're doing about 80, and you're like, oh shoot, what's that up there? Might as well slow down a little bit. So you slow down a little bit. Okay, so, but your average rate of change, so your average speed really, is going to be like somewhere in here. So that might be if you add everything up, that might be your average. Okay, so we're actually not so much interested in that because that's just overall distance divided by the time it took you. So if it's, it's 100 miles and you get there in, 100 miles, it takes you an hour, or no, 2 hours, then you went 50 miles per hour, right? That's how you would calculate that. Your average is 50 miles per hour. Obviously, you're going to speed up and slow down as you go. Example I like to look at nowadays is when I'm traveling, I see the speed limits on these interstates out there in Utah and parts, well, not Colorado, but parts of Utah. It's like 80 miles an hour across I-70. And I have a truck and trailer, so there's no way I'm doing 80 miles an hour in that thing because I shouldn't be. So I don't look at what the mapping programs are telling me. I have to actually look at the mileage and guess my average speed, right? So that's how you're looking at this. We want to talk about not average speed. We want to talk about instantaneous rate of change. So that's how it is defined. So the instantaneous velocity, so that's how we're going to say it. Instantaneous velocity is s prime of t, which is equal to velocity, v of t. Or you could write it as ds dt is equal to that limit above. So it's the limit of f of t plus delta t minus f of t all over delta t as delta t approaches 0. Then, so that has like a direction to it. If you take, so right now, so it might be positive or negative right now. It's still slope, so the slope could be positive or negative. So if you take the absolute value of that, then that's referred to as speed. So absolute value of s prime, or the velocity, is defined to be speed. Okay, then what is the rate of change of velocity? So you're traveling at, heading to Vegas, you're traveling at 60 miles an hour. 60, that's like if there's traffic, right? So you're traveling at 75 miles an hour, just a tick over the speed limit here in California, and on the interstates, and then you take off. Like, all of a sudden now you're going 80 miles an hour because you don't want to get passed up so much by all these people. You don't want to be passed up so quickly by all these people. So when you went from 75 to 80 to speed up to go with the flow of traffic, which is basically what happens these days, we call that what? That's acceleration, right? So the rate of change of velocity is acceleration. I forgot the is, didn't I? Okay, so when you do s double prime, so you take the prime again, and I have to get into multiple derivatives here, but thus the rate of change, or take the derivative of velocity, that's acceleration. We use a of t. Okay, so and we're going to be just taking, we're not going to be doing the limit definition so much on this at all. We're going to just be taking derivatives. So all I have left, really, I mean, that's really it. There's a lot more to that section, but this is all I need you to know. Like, you just need to know if you're given a position function, s, where's my s, like that, or f of t, then its derivative is velocity. Its second derivative is acceleration. Okay, that's what you need. Okay, so let me highlight right here. So position function, abbreviate s of t. Velocity is s prime of t, which we say is v of t. And then acceleration. Acceleration is s double prime of t, which is v prime of t, which is a of t. This will make this look pretty since we're here. And then acceleration. Okay, let's look at an example now. These are usually pretty straightforward stuff, just finding, given something, find velocity, acceleration. Okay, so let's look at this example. This is number 2 in the book. S is given by 6t minus t squared. T is in the interval from 0 to 6. So you can say like t0, the first value is at rest. And then you go from there. So I just realized I need to read the question. Yeah, I need to read the question. So this is, I totally forgot about that. Short video, so we'll just keep this one going. 3.4, so go to 3.4, number 2. And I'll maybe just roll with it here. 3.4, number 2. Basically is saying, when they call these, the particles, they call them bodies. When they say the body's in motion, that's what they mean, is it's really just like a particle. So find the body's displacement and average velocity for the given interval. Find the body's speed and acceleration at the endpoints of the interval. When, if ever, during the interval does the body change direction? So let's take a look at that. You'll see how I do this now. Just, why not? Okay. I think I meant to do this. Well, we can just there, do it like this. Try that again. So that's the question, which will allow us to go through this. We'll use the video. It's a little crooked, but we'll figure it out. Then I go in and crop it. Like this. We can put a few up there. Okay, so let's go through this question now. Now it's all there. So, this is sort of the thing. If you know you're going to be finding velocity acceleration, just start taking derivatives. It kind of makes you feel better. So let's go ahead and just do S prime. So S prime is just going to be 2t minus 3, derivative of constant 0. Oops, I'm at the wrong one. I did 1. We're doing 2. I knew because the interval was wrong when I was looking at it. So, okay, so S prime is just 6 minus 2t. S double prime is negative 2. So it's basically a constant acceleration. Or, and let's use the notation v. So v is 6 minus 2t, and so a would be negative 2. All right, so then the first question is displacement and average velocity give on the time interval. So that's your deltas. Okay, so that's basically your delta S over delta T. So your average, let's come down here. Let's change colors, come down here. So your average then is, so A, you do your delta S, which is S of 6, the endpoints, minus S of 0. So you calculate that out and you get 6 times 6 minus 36 minus 0 is equal to 0. So there's no displacement, basically. When we can talk why, that looks like a parabola to me. Maybe it just goes up and comes back down to 0. Okay, then you're, just for sake of doing it, your displacement is 0, but so would be your average rate of change. So delta S is 0, but then you get 6 minus 0, so then it's just 0 over 6, which is, of course, still 0. So that answers question A. Find a body's displacement and average velocity. So the average velocity is 0 in this case. Okay, now, B asks the question, find the body's speed and acceleration at the endpoints of the interval. Well, you just calculate that. We already calculated V. So the velocity is V of 0, which would be 6 minus 0 is 6. And then V of 6 would be 6 minus 2 times 6, which is negative 6. So speed is going to be the opposite value of velocity. So in this case, you get opposite value of negative 6, which is equal to 6. Okay. So that's at the endpoints. And then let's see. When, if ever, during the interval does the body change direction? So that's really kind of something we're going to get to much more carefully later. But if you graph this thing, this is the sort of stuff we're going to start analyzing. So C, you're looking at S is 6t minus t squared. That can be factored. T times 6 minus t. Okay, so t it's 0 at 0. So these are the like the roots of that. And then at 6. And so what you're getting then is this parabola. That didn't do that right. So we're getting this parabola 0 to 6, 2, 4, 6. We'll have to just make this smaller. And it's upside down. It's shifted over, but it would change direction if the velocity is 0. So if you look at S prime is, what is that again? What was S prime? Where's S prime? S prime is 6 minus 2t. So if you set that equal to 0, you get t equal to 3. So when t is equal to 3, you just solve that. You get 3, so 2, so 3 is right here. You get the velocity to change. So that means it's 0. So what that is that vertical tangent line. So up here, and it goes up to, well, we'll find the value. So S of 3 is 6 times 3 minus 3 squared. So 18 minus 9, so 9. So 2, 4, 6, 8, 10, so it would be right about here. So here's your graph going up and then back down like that. There's your, we know it's a parabola, so it's doing that. And that's it. So you have this horizontal tangent right there where it changes direction, where the velocity is 0. And that's going to be a standard like concept we're going to be looking at, what we're going to find. So when, if ever, during the interval does the body change directions? Yes, it changes direction at 3. So at 3 changes direction. Okay, so I kind of did that by graphing, did that by analyzing the derivative. And that's one thing we're going to look at much more carefully in chapter 4 is when the derivative is 0, you get basically a maximum. You get a maximum, what's called, we're going to define it to be a local maximum or relative maximum or minimum for the curve. So that's getting ahead of ourselves. Okay, what else on there? Let's see. So try number 8. Okay, so number 8 in the book. And take a look at that. I'll read it to you, but I'm not going to take pictures. Well, I could take a picture real quick. Why not? We're doing this one a little differently today. So, oops. Yeah, well, that'll work. So number 8 is this question. So let's use that guy here. Let's go ahead and crop that. Like that. Let's make sure I got all of it in there. Yeah, I did. Okay, at time t greater than 0, the velocity of the body, so like particle, along the horizontal s-axis is v equal to t squared minus 4t plus 3. Find the body's acceleration each time the velocity is 0. That should say 0. When is the body moving forward, backwards? When is the body velocity increasing, decreasing? Okay, so I have some written up, and then I want you just to do the rest. We're not going to go through all those details in here. So go to, I'm going to just copy it over. This one is way off, wasn't it? Let's see. So this is number 8. So you want to look at all those questions, and I have most of them written down, but not all of them. So do the rest on your own. If you have questions about it, you can ask me later. Okay, so this one gives you your velocity. Obviously, you take the derivative. The velocity changes around 1 and 3, and there's your acceleration. And then B and C. So usually this is something I have you do on your own, or in class, like together as groups. So try this, try it. And this time I'm not going to go through it unless you want to do it individually. Thank you.